So today we're going to be looking at a lot of different packet examples just in general. We're sort of going to be doing a lot of practice with what we talked about last week, which is finding limits and determining continuity and proving continuity and things like that. So it's kind of like almost like the part 2 of what we did last class and some more review from last year. So in general, if we're trying to solve for a here and to make f of x continuous, what's like our method of doing that? What do we need to do to make it continuous at x equals -1?
Do the first equation equals -1?
Set the first equation equal to -1?
Yeah.
Do we agree? You're doing this. Why?
Replace the x.
Okay, replace the x with a -1 on the left side as well.
Yeah, that's it.
And make this equal to -1? Okay. So, yes, I would agree with that. This -1 is coming from where? Where's the -1 on the right side coming from? Henry? The x, yes. Yes. Okay. So what we've done is we've substituted -1 in for both x's and then set the two things equal to each other. That's our method here. Because this would be like the left-hand limit, and this would be the right-hand limit. And we've substituted in the x value that we need, and we're setting them equal. Okay, so now we can just solve for a. And we get a equals -3. Okay. For a question like this, we don't need limit notation.
Because it's what value?
Yes, exactly. And so I'm just going to try to be extra careful, especially the first few weeks as we're getting used to, well, I'll always be careful about notation, but just trying to point out when you need to write limit notation and when you don't. We don't need it here because it just says what value makes f continuous. Same thing in number 13, find the constant so that the function is continuous. Where we're going to need some limit notation is going to be in number 11, because it says use the definition of continuity to prove or disprove that f of x is continuous. So this is when we need limit notation. Okay, so let's look at number 13 here. So here we have a function that is basically defined by this for every value except a. But then at a, the function is defined as 8. So we're looking for whatever this value a is. Why is this function here defined like that for everything except a? What's wrong with a at that point?
It's a removable or a hole.
Yeah, we'll get a hole there, exactly. Yes. So we plug it in, we plug a and we get 0/0. How do we solve for a? What should we do here? What do we got? What could I do first? Turn and talk to your neighbor. What would you do first here?
Then you end up with a equals ES after
Okay, let's bring it back. Let's talk about what's going on here. So we have a removable discontinuity at x equals a, because when I plug in a, I get 0/0, and I also know that if I factor, oops, not like that. If we factor the top there, we can have our removable discontinuity cancel out. So there is a hole, And so basically what we have is some graph that's a line, because a is a constant here, with a hole in it. And we also are told that at this value, whatever it is, x equals a, we have a coordinate, let's say it's 8. We have some point there. So right now, would this function be continuous? No, it's only going to be continuous if what is true in this picture. How would I change the picture to make it continuous?
Four lines, like filling the hole, I guess.
Yes, exactly. Like if this line were up here, like that. Oh, that's kind of nice. I can just move it, right? So we need that line to be up there at 8. And the x value there is x equals a. So what we need is, we need x plus a, that's this line, to equal 8 when x equals what? A. So we need a plus a to equal 8. We need a to equal. Yes. We need a to equal 4. So that's what we have to do. We basically have to make these two things equal when x equals a. And one of our steps is going to involve factoring and canceling out that removable discontinuity. Again, we don't need limit notation for this one. Okay.
How'd you get a plus a equals a?
So I have x plus a equals 8, and then we're taking a and plugging it in. Yeah. Okay. Let's look at number 11, because number 11 is going to highlight how we need to use limit notation to prove continuity. And because it does get, this is a little picky right here. So first of all, let's just look at x equals 1. Is this graph continuous? Let me just go ahead and draw the graph. And I know it's kind of faded on your paper, so it's supposed to be there. That's a little hard to see. Here's x equals 1. Here's x equals -1. Is f of x continuous at x equals 1? Yes. Yes. We can look and see there's no break in the graph right there. So here's what we need to do. We need to say, in no particular order, but we do need to say them all, what does f of 1 equal? 1. We can see that from the graph. For this one here, I'm looking at a graph. I can tell what the limit is as x approaches 1. I don't need to do separate left and right hand side limits, because I can just look at the graph and see what the limit is. What is the limit as x approaches 1?
1.
It's also 1. So does the limit equal the y coordinate? Yes. So we can say, therefore, f of x is continuous at x equals 1. If I want, just as a little bonus, I could make sure to like put an equal sign in between these two here, or actually the way that Miss Moy shows this in BC, I kind of like this, so maybe I'll pivot to doing this. Is she'll write like the limit of f of x as x approaches 1 right here, and if since they're equal, then she'll put that equal sign in between them there. But if they weren't equal, she would put a not equal sign in there. So that's one way that you could do that. It's not necessary, but seeing that they both equal 1 is enough to prove that f is continuous at x equals 1. Is f of x continuous at x equals -1?
No.
No. Why? Okay, we have a jump discontinuity. So how could we explain that using limit notation, or just using the word limit?
It approaches two different numbers from left, so limit f of x -1. I don't know. However you say from the left is -1, and from the right is +1.
Yes. Yeah, the left and right hand limits aren't equal. That's how you say it, remember, with a little minus sign or a little plus sign. This is from the left. This is from the right. You don't need to write those things down. That's just me reminding you. And then if I want to throw a little not equal sign in there, I can see that they're not equal. -1 and 1 are not the same number. So I don't need to say anything about the y coordinate, because is that enough to prove that it's not continuous? Yes, it is. So we can just say, therefore, f of x is not continuous at x equals -1. That's all we need. We could also throw the y coordinate in there too, but we have enough information right there.
Can I say discontinuous instead of not continuous?
Say not continuous.
Okay.
Yep. Say not continuous. Okay, so this is just you're gonna see this sometimes. You're gonna see this kind of notation where you have to prove continuity, and especially once we talk about IVT next class. So I know some of you guys saw IVT last year in AP Pre-Calc, but some of you guys did not. So that's okay. I'll teach it like it's brand new. Okay, let's do some more practice with that. I want you guys to do number 15 on the next page. Take a few minutes to do this, and we'll go over it. So just to give you a little direction here in case you're not sure how to present your answer, in order to answer this question using the definition of continuity, we need to find all three of these things. So we need to figure out, and we need to show work of where we got these things, but this is basically what we're trying to answer. So if all three of these things are equal, then we've done it, it's continuous, and if one of these is not equal to the other two, then it's not continuous. So this is to give you a little direction here. We'll take another minute or two on this. Okay. So what we don't want to just do is say something like that equals 4. We need to show where that comes from. So how do we get g of -3? Where do I plug -3 into? F of x, right? Because right here, this is where x equals -3. That function is defined by f of x. So even just saying something like this, g of -3 equals f of -3, which equals, now, we could skip showing where we're plugging in. We know we're plugging into f of x. So if we just say in our heads, like, okay, it's the square root of 25 minus 9, which is square root of 16, which is 4, that's fine. If we want to show the work here of plugging that in, that's fine too. But we need some connection to say, okay, g of -3 comes from f of x because of how the function is defined. So now we can say it's 4. So just like a couple steps, 1 or 2 steps to show where I'm getting that from. Similarly, as we approach -3 from the left side, where are we plugging in -3 to get the left-hand limit? Yeah.
But if you plug in -3, wouldn't the negative in f of x become positive?
It's 25 minus x squared, so -3 squared is 9.
Isn't a minus negative the same as a...
No, it's 25 minus 9, because if we square -3, order of operations, right? So we do exponents first.
Okay.
So where do we get the left-hand limit from? For g of x. Well,
The x plus 7.
the x plus 7? No. That would be the right-hand limit.
The 25 minus x squared.
Yeah, exactly. So this would be our left side, this would be our right side. So yes, we could do the same thing here. We could write either f of -3, or we could write root 25 minus 3 squared. We don't need both of those. We could just write 1. We've kind of already shown where that's coming from over here. So that's also 4. Then for the right side, we just want to write negative 3 plus 7 to show where we're getting it from. We're getting it from this part right there. And then we can say this equals 4. So is g continuous at x equals negative 3? Yes. Notice I don't have to say anything like because g of negative 3 equals this. Like we've shown that they all equal 4. If you want to be extra specific, you can put equal signs in between those things. You could put equal signs over here just to show, but if it's all 4, we can see that they're equal. So I don't need another sentence to justify my work. My work is justifying my answer. And so this is just, basically I'm trying to introduce you guys to how you get full credit for things in AB calculus, because sometimes it can be a little bit confusing. How much do I need to do? How little? You very rarely need to write a whole bunch. Let me just write that down. I'll say for like each question that you're answering, if it's an FRQ, it's 1 sentence or less that you need to use. If you're using 2 sentences, you're probably talking too much, and honestly, there's a chance that you might say something that's wrong. So AB Calc's a little bit minimalistic when it comes to the words that you need to use. It's the math. Like, this is your justification right here. And this is just your conclusion. Let the math do the talking. That's good. Let me write that down. Let the math do the talking. I gotta remember that for my other periods. Aiden.
Why is the answer 4? Because isn't 25 minus 9 14?
16.
Oh.
Yep. Okay, questions on this? Okay, we're going to move into some more limit examples on the next page. So these are just some classic limit problems from last year. We're going to skip number 1, but I want you guys to do numbers 2 through 5A. Don't do 5B. You don't know how to do 5B. You might, if you think you do, you probably don't, because I need to teach you how to do that when we do tricky limits. Take a minute here to check in with your neighbor if you haven't yet. See what they're getting, see what their method was.
Because some of the log is still what the power of that equals. When you put 1 in for every number that's 0, you have to ensure the ln of 1 is 0. I think.
All right, guys, let's check these. So what should be our first method for finding our limit? What's our number 1 go-to? Just plug it in. Yeah, substitution. We plug in 1. We get 1 over what? What's ln of 1?
0.
ln of 1 is 0. So 1 over 0. This means the limit does not exist. Is non-existent. Right there. So if we get 1 over 0, we just say DNE, or in this case, it's multiple choice, so we circle non-existent. Okay, if we plug in a to number 3, what do we get? Just if we plug it in straight away. We get 0 over 0. Okay, so that's a problem for us. That's when we need to do something. What should I do? Factor. Factor which part? The bottom. How does the bottom factor?
X squared minus a squared times x squared plus a squared.
Nice. Yeah, so we can factor the top using difference of squares, but the bottom also factors using difference of squares and helps us just cancel out the entire top. Notice I still have my limit notation right here. Now, on a multiple choice question, it won't actually matter. You don't need to show proper notation, but I'm showing you the proper notation so that you remember. Until we plug in a number, we have to keep the limit notation there. Am I able to plug a in for x now? Yes, we get 1 over a squared plus a squared, and so that is letter B. Notice I got rid of the limit notation here because I plugged in the number for x. So once we substitute, we can get rid of limit notation. Okay, in number 4, if I plug in 0 for x and do f of 0 minus f of 0 over 0 squared, what do we get? Yeah, well, that'd be 0 over 0.
So I factor.
So we have to do something. What do you mean factor? What can we do with number 4? Because we're getting 0 over 0 right away. We plug in f of x. Okay. So replace f of x with 2x squared plus 1. What is f of 0?
1.
F of 0 is 1. And now we can start to simplify. So those 1s will cancel. The x squareds will cancel. What are we left with? 2. Okay. Questions on any of those? So just remember, anytime we get 0 over 0, we have to do something.
Could you go over this again? I could not see that.
Number 4?
Yeah.
So once we substitute in f of x and f of 0, we can see that our 1s are going to cancel. And so it becomes limit of 2x over x squared. And the x squareds will cancel. And so it just becomes the limit of 2 as we approach 0, which just equals 2. Okay. Number 5, we're just going to do part A. So with composition of limits, actually we're going to look at the limit laws in just a second. But what we do is first we do the inside. What is the limit as we approach 0? 1. And then we just do that for the outside. We actually just evaluate f of 1. What is f of 1? 2. We do this if there's no discontinuities. So we noticed that at 0, f is continuous, and at 1, f is continuous, so we just do inside then outside. If we were to do the same thing for the part B, what I'm noticing is if we do the inside first at -1, there is a discontinuity. The limit is 2, and then as we go to 2 for the outside, there's another discontinuity. And so we're going to have to come back to this. This is a tricky limit. The answer, by the way, is 5. So if you got 5, then you do know how to do this. But if you didn't get 5, then you got to wait a couple days till we do section 1.6. So that'll be next week. Those limits are tricky, let me just tell you. So we'll come back to that. Okay. Let's go to the next page and look at our limit laws. So, with these limit laws, the key here is, excuse me, this has to be true. Both functions have limits that exist. At x equals c. It's the same x value for all of these. When this isn't true, we're going to do tricky limits because they get tricky. So assuming both of these limits exist, so just a couple things here. If the number is a constant, that just represents a horizontal line. So the limit at any point is just going to be whatever that constant is. That could be e, that could be pi, that could be 2, whatever. Basically, other than that, to get a lot of these, we're just substituting in and taking the limit values separately. So for example, the sum rule here, if I have some combo function, let's say it's 2x plus 1, I'm trying to find the limit of. This is the same thing as finding the limit of 2x and adding it to the limit of 1. Separately. But what we're just doing is we're just plugging in the number for x. So a lot of these aren't like crazy mind-blowing, but that's just what that limit law means. H is the one we just looked at. So notice it's the limit of the inside plugged into the outside function. Okay, do number 6, all the parts. Ready, set, go. Okay, so our limit laws say, first of all, do both of these limits exist? Yes, they do. They're at the top of the page there. Is it the same x value? Yes. So if I do limit of f plus g, it's the same as the limit of f plus the limit of g, which is 4. Yeah, it's just 7 plus negative 3. For the next one, 7 times negative 3, negative 21. 5 times the limit of g, negative 15. And then the last one's just negative 7 over 3. So because those limits exist, and it's the same x coordinate, we're just doing math with the limit values. For letter E, that's using both of these graphs. First of all, for f of x, does the limit exist as x approaches 2? Yes, what is it?
1.
Yep, it's right there. And then does the limit exist for g?
Yes.
Yeah, what is it? 3. So 1 plus 3 is 4. Questions on this? Okay, let's go to the next page. Do number 7. Okay, pause for a sec. Do these limits exist? At h, f, and g. Do those limits exist as x approaches 3?
Yes.
Which column are they?
Right.
The right column. Do not use the left column. We want to use the limits. Since these limits exist, we should be using those limits. So we use our h of x, the limit is 2. 2 times f of x is 2. 3 times g of x. Also, one fun thing about AB Calc is if you're doing an FRQ question, you can leave your answer like this. You can leave your answer unsimplified as long as it's all numbers. Like you can't leave this in your answer, you'd have to say that that's 1. But you can leave your answer unsimplified. For FRQs. So like that'll only apply to us like on our quarter test when we're doing FRQs, and we'll do practice FRQs as well. But you just so you know, that's a fun part of AB Calc. On our quizzes and tests, I'm going to have you guys simplify completely, so that does equal 56. Yeah, so again, if we're doing math with limits, we need to make sure we're doing math with limits and not the y coordinates there. Any questions on this one? Okay. We don't need this. Let's just talk about limits at asymptotes. It's not, we're not getting 0 over 0 here. We're getting something over 0. Like, for example, the first one we're getting 1 over 0. Except for number 11. So these will be quick, don't worry. We saw one of these in the multiple choice. If we're getting a number over 0 for our limit, what do we say the limit is? Does not exist. Yep. DNE, DNE, DNE. That's it.
Can you write infinity or negative infinity or something?
You can, but it has to be correct. So if you say the wrong infinity, then it's wrong. If you just say DNE, it's always going to be right. So just say DNE. Is my recommendation, my professional recommendation.
If it's something over 0.
Something over 0, the limit does not exist. Yep. I'm going to come back to some of these other ones. But I want us to jump ahead to page 13. So we have that little box right here of 9 things here. Notice now what we're doing is as x approaches infinity, so we're talking about end behavior. Oh yeah, it says that right there. You can just underline where it's bolded, end behavior. LOL. Okay, so notice the method here, using what you covered in pre-calculus about different functions. Basically what we're just trying to do is picture what's the graph doing. What do these graphs look like? Or you can think about plugging in infinity for x, or really, really big numbers, like a billion. And what's going to happen with some of these graphs. And so, for example, like absolute value function, can you guys show me with your hands what that looks like? Yeah. Okay, we got one of these. So as we approach infinity, what does the function approach? Infinity. So our limit does not exist. Yep, that's how we want to answer these. You guys answer the rest. Ready, set, go. Okay, turn to your neighbor. What do you get for numbers 1 through 9?
Like 100 or something.
Oh, yeah. So, yeah, and then it would just like kind of cancel out.
I mean, I forget what the first term, like that's even.
You would say it does not exist because it's not approaching any one number, it's just going back and forth. So,
You know, this is
Yeah, if they're
4,
the
this is
same.
2.
Yeah, 63.
Well, 8, it's like the best.
Oh my god.
What do they do again? Yeah.
so it's basically you have a horizontal asymptote at 5 points. So that's what
So that determines horizontal asymptote?
which is the end behavior, which is the limit.
What about the 8?
Yeah, it's that x over.
Does not exist.
Yeah, it's top heavy, it's going to infinity.
Wait, what does that mean?
It does not exist.
It would have like a slant asymptote.
Oh, a slant asymptote.
Yeah, you have something that's like kind of doing that. But it's approaching infinity.
If it's approaching infinity, you're just right, does not exist.
Exactly.
Wait, really? I thought you just said, or like y approaches infinity.
Anytime we're going to infinity, that we just want to say the limit does not exist.
Okay.
But we're simplifying that. That's all we need to do. Calc.
How'd you get 0 for 1?
Because it's volume. Okay, yeah.
If it's bottom heavy, it's 0.
Oh, wait.
You know, like number 9. Yeah. So for 9, it's going to be 0.
Here's what we should get. As we look at number 12, those are the same degree. They're both x squared. the top and bottom will both always be positive as well, because it's x squared is always positive, x to the fourth is always positive. So it's the same degree. The coefficients of both are 1, so we just approach 1 in both directions. In number 13, these are also the same degree, because we have x compared to square root of x squared. But x on top is not always going to be positive. X squared on the bottom will always be positive. So as we go to negative infinity, we go to -1. So this is the one that's different. But as we go to positive infinity, we're still going to equal positive 1. It's basically like x over x, except the bottom's always positive and the top could change.
What makes it different from 10 being positive?
10, we are going to positive infinity.
Oh,
Yes.
okay.
So that's like the second part of 13 there. Yeah, yeah. Good cue. Okay. We're going to look at a few more examples together as a class, and then I'm going to have you guys do something else. I'm going to have you do something else. We're going to look at this function dominance page right here. We're just going to look at number 15. So, you may or may not know this, but different functions grow at different rates. The fastest growing functions are exponential. The second fastest are polynomial. So exponential would be like 2 to the x. Polynomial would be like x squared. And with polynomial, the higher the degree, the faster it grows. Then would be like the root functions, like square root x. And the slowest growing functions are the logarithm functions. Any log. And this determines basically function dominance. The faster it grows, the more it's going to influence a function's behavior.
What about stuff like sine of something, like sine of x?
So those don't grow. Those are periodic functions. They're not growth functions. So they just basically alternate between the same values. So they don't apply to this. So when we look at number 15, we notice we have a polynomial function on top, an exponential on the bottom. The exponential is going to grow faster, so this function is bottom heavy. Heavy. Which means as we approach infinity, our function is approaching 0. Yep. Number 16, we have e to the x on top. That's exponential. That's the fastest growing one over the slowest growing one. So this one's top heavy. As we approach infinity, what would we say is true of the limit?
Doesn't exist.
Does not exist, exactly. Okay, cool. Okay, I have something that I'm going to try and squeeze in the end of class, and we'll see if it works. But probably I just need to go faster in my other classes. I'll probably just always learn that in first period. Okay, back on page 12. Not yet, but in a second, you guys are going to get into groups of 4. You're going to do one problem each of these. 1, 2, 3, 4. Now, if whatever problem you pick, you don't actually know what to do, you can get help from your group mates. It just has to be your handwriting. Okay, you have to be the one actually writing it. These are all going to be on one piece of paper, though. So you can solve it on a separate piece of paper, but then you're going to copy it down, and you're going to turn that paper into me at the end of class with each of your names on it in 4 boxes. Does that make sense? Your paper is going to look like this. 4 different handwritings, 4 names, You can work together on all of these. It just has to be your handwriting for one of the problems. Okay? Ready, set, go. Find a group of 4. You can change seats. And if you need an extra paper to write on, you can come get it from me. There you got there 4. Who still needs a group of 4? 1, 2, 4. You got 2 or so. Where's the group of 4 right here? You got them. You got them. Stand up if you still need a group of 4. There we go. Look at that. You guys can get a group of 5 right here. Yeah, if you guys want to bring your chairs over, if you guys want to go to the back too, perfect. You want to go.